So good evening all. So welcome to the fourth week's problem solving session on modeling and simulation of dynamic systems. So my name is Parth Joshi. I am a PhD student in the Department of Mechanical Engineering at IIT Bombay. And as the recipient of the Prime Minister's Research Fellowship, I got an opportunity to interact with you for these weekly problem solving sessions. So I've been conducting these sessions for the past 4 weeks, past 3 weeks, and now we come to the fourth week's problem solving session. So where we'll be discussing about these following, like the problems related to these following things. So the first section is linearity and non-linearity in systems. So in this section, we basically discuss about the general uh, way to linearize the non-linear behavior of systems about a particular operating point. So in many practical systems, the governing equations tend to be non-linear. So some of the examples which have been discussed are like flow through orifice or thermistor. So in these, the differential equations which govern the characteristics, so they are non-linear. So the procedure to linearize these system equations about a particular operating point is given. So we basically uh, take a certain chooses a particular operating point now depending on our requirements. So generally in control systems we would like to control the behavior of a systems about a particular operating point. So and we generally want to uh, have like small we are interested only in the small variations about that operating point. So therefore this particular concept of linearizing the governing equations works well for many practical applications. So then the next section is about system models of rotary plus translatory systems. So where we generally discuss about the examples like rack and pinion and pulley and cable systems. So where for example in rack and pinion we have a motor or some actuator which is rotating a pinion, and then uh, this is basically the pinion is engaged with a rack which has again teeth, and this rotating pinion is moving the rack back and forth. So basically rotary motion is converted into translatory motion. So it can also be other ways where the rack is actuated and the pinion may be rotating. So it can also be the other way, but generally it tends to be that the pinion is rotating and the rack is moving. So this particular mechanism is used in the steering wheel systems of passenger cars. So this is commonly used mechanism in many other industrial applications also. Then we are also discuss about pulley and cable systems where pulleys are rotating elements and the cable systems are basically, so the cables are being passed through over the pulley, and by rotating the pulley the objects which are suspended through the cables, they can move up and down as required. Then in the next section we discuss about system models of electromechanical systems. So the examples such as potentiometer and electric motor have been discussed, so which involve basically the combination of electrical and mechanical, or the conversion from electrical or to mechanical or mechanical to electrical energy. So in the potentiometer, basically the mechanical movement, let us say translation or rotation, is being translated into equivalent electrical, let us say the potential difference. So in case of the potentiometer, the potential difference at the output is proportional to the rotation of, let us say in case of a rotary potentiometer, it is proportional to the rotation, where or in case of a linear translatory potentiometer, let us say like a rheostat. So there the amount of sliding, so the potential difference across the terminals depends on the amount by which we slide the movable terminal of the rheostat. Now, we have also been like discussed about the uh, model for the electric motor. The governing differential equations have been derived for the DC motor. So the main two cases where it has basically the DC motor has armature and field windings. So there, instead of using permanent magnets for the producing the magnetic field, we can also have use coils to produce the equivalent magnetic field. So in the DC motor, we can have either armature controlled or field controlled DC motor. So in case of armature controlled, we basically keep the field current constant and vary the armature voltage to control the DC motor. And in case of the field controlled ones, we keep the armature current constant and vary the potential difference across the field windings. So these cases have been discussed and the governing differential equations have been derived. Then the system models of hydromechanical systems have also been discussed. So with the considering the example of a hydraulic servo motor. So this has been taken as an example to illustrate the system model. So where we have hydraulic pressure being converted into mechanical movement. So basically using uh, pressure difference across a piston cylinder to create mechanical movement. So so in case of a hydraulic servo motor, we can have like the pressure difference across the ports or like of the cylinder, inlet and outlet ports to create basically the pressure difference basically creates a force on the piston, and this piston which may be connected to a load, so it will create basically mechanical movement of the load because of that. And also system models of robots have also been discussed. So but today we'll be focusing on the problems related to these four sections which have been discussed over here. So let us come to our first uh, problem. So So the first section which we just talked about deals with the linearization of differential equations. So let us consider the uh, problems. So first, let us take the example of a simple pendulum. Now, how to linearize basically the differential equations and use this approach to solve the equation for a simple pendulum. So we'll be discussing about that. So now, so let us first draw the diagram of a simple pendulum. So let us say the pendulum is suspended and let us say this is the bob of the pendulum. So let us say the pendulum bob has a mass m, small m, and let us say that the angular displacement with respect to the vertical for the pendulum is, we call it as theta, and let us say capital L is the length of the pendulum. So now let us first derive the basic differential equation for the simple pendulum. So for that we have to apply the Newton's second law of motion. So so let us first draw the free body diagram of this pendulum. So the forces acting on this pendulum would be firstly the weight of the pendulum bob, mg, and then there will be a tension force acting on the pendulum because of the string or the rod, pendulum rod. So there will be either a tension in the rod or the string. And so these are the only two forces. Now if we neglect air resistance, so then that would also be another force. But now for now, let us say if we neglect the air resistance, so then we can these will be the only two forces acting on the simple pendulum. So now we can now proceed with the derivation of the differential equation. So we will write the equation for the Newton's second law of motion. So in so for that so we will basically use the we can either use the Newton's second law of motion, or we can also consider the moment, take the the moment about the pivot P, let us say, about which the pendulum is suspended. So we can, let us say, use the other approach where we take the moment, so that would be simpler. So the moment of the pendulum forces like acting about the pivot. So the net moment about of the forces about this pivot P, that is sigma mp, what we have written is basically the this particular force tension will pass through the pivot because it is acting around the rod or the string, so therefore which passes through the pivot. So therefore the tension T will not cause any moment about the pivot. The only force that will cause the moment would be because of the weight. So the horizontal distance of the pendulum bob from the vertical is L sine theta. So the moment about the pivot would be basically minus mg into L sine theta. And this moment is equal to the moment of inertia about the pivot into theta double dot. So what would be the moment of inertia about the pivot P? So it will be, now we will now consider that this particular mass small m is actually a point mass. So therefore the uh, moment of inertia about the pivot will be m into L square. And if we assume that the rod is massless, now if the rod is not massless, so then we will have to add the moment of inertia of the rod. So let us say if the like the rod is not massless, so then so the moment of inertia of the rod has also needs to be added. So if the rod is massless, so then we can neglect it. So let us say if the mass of the rod is so m rod, so then this particular quantity moment of inertia of the rod, we can write it as mass of the rod into the length squared by 3, so which is about the pivot. So yeah, so this is what like generally we can write the moment of inertia. Now we come to the basic equation of motion, so which is moment of inertia into theta double dot is minus mgl sine theta. So now we can substitute the equation for the moment of inertia. So what we will get is, so this will be the equation of motion for the pendulum. So we can rearrange the terms and write it as theta double dot into m plus minus mgl sin theta. So therefore we get the equation as theta double dot plus g by l into m upon m plus m rod by 3 sin theta is equal to 0. So this is like a non-linear second order differential equation because sin theta is a non-linear term here. So now what we do generally to linearize this particular differential equation. So we generally assume small oscillations or theta with respect to the vertical. So for that we generally assume sin theta equal to nearly equal to theta, and then this becomes a linear second order differential equation with constant coefficients which can be solved easily. So we know the general solution for this. But now how do we actually linearize this particular differential equation? So for that we again bring in the Taylor series concept. So for that, as we have like discussed in the lectures, so that um, we generally to linearize a function we write the Taylor series of the for the function about a certain operating point. So here our equilibrium point is basically theta equal to 0. So let us say for like a simple pendulum which is suspended vertically like this, so the equilibrium point is again theta is equal to 0. And so for this we consider, let us say, the Taylor series for the function sine theta. It comes out to be basically theta minus, and so on. So basically these are the this is generally the Taylor series for the sine function sine theta. So now this is like a well-known series for the sine and cosine function. So for this for small oscillations we assume sine theta is nearly equal to theta. So therefore we neglect the higher order terms, theta cube, theta to the power 5, theta to the power 7, and so on. So then our differential equation becomes theta double dot plus g by L into mass of the rod by 3 into theta is equal to 0. So this is our usual differential equation which we consider, but it is an outcome of the using the Taylor series expansion. So this is the the common example that we must have come across many courses in physics or in vibrations, etc. So this particular example we have been studying since a long time, but this is another example where we use the approach of linearizing the differential equations to get a linear second order differential equation which can be solved easily. So yeah, so this was the example on linearization of the differential equations. Now we come to the next question where we have to derive the relationship between the input torque and the output velocity for the rack and pinion arrangement, which is shown in the figure below. So R is given as the damping coefficient between the rack and the guide. So let us first draw the free body diagram for each of these components. So let us first uh, draw the free body diagram for the pinion. So for the pinion, T in is the input uh, input torque which is acting on being supplied from some motor or some actuator basically. Then because of the friction in the bearing, so let us say the shaft speed is omega or theta dot or whatever. So we will assume that the torque of resistance provided, or basically the bearing friction, so that torque is represented as RB into omega, which will be opposite to the direction of the rotation. And then the pinion is in contact uh, with the rack, so there will be some forces acting on the uh, basically the pinion will basically exert some forces on the rack, and the rack will provide a reaction force, and so because of that, so there is a net output torque T out that will be acting on the pinion. So then so the basically the force that would be acting on the rack because of this particular pinion, so that will be basically, so let us say that force F will be output torque divided by the radius of the pinion, so that will be the force acting on the rack. So let us draw the free body diagram of the rack. So this, let us say, is this is the direction of the velocity, then the friction force that is acting on the rack will be R into V. So let us assume that R is the coefficient of viscous damping. So it will be proportional to the velocity, and the direction will be opposite to the velocity. And another force that is acting on the rack is because of the force because of the pinion, so which is this force F. So now we have basically drawn the free body diagram for this pinion as well as the rack. So let us now proceed with the derivation of the differential equation. So first let us write down the differential equation for of motion for the rack. So we have to apply the Newton's second law to basically get the sum of net forces on the rack as well as pinion is equal to the mass into acceleration. So for the rack which has mass small m, so m into dv by dt is the mass into acceleration, so which is equal to the net force acting on the rack, which is the force F because of the which is exerted by the pinion minus the force acting on the rack because of the movement between the rack and the guide rails. So which is the damping coefficient into velocity, which is RV. So this is the damping force. Next we come to the equation for the rack, for the pinion. So here basically the, let us say we assume that the inertia, moment of inertia of the pinion is IP. So then the equation of motion for the pinion will be moment of inertia of the pinion into the rate of change of angular velocity omega I into d omega by dt is equal to the net torque that is acting on the pinion. So which is basically the input torque minus the bearing torque, resistance torque because of the bearing friction. Minus the opposite torque that is being applied because of the load, or which is basically T, the output torque T out. So these are the two, uh, basically the torques that are being acting, and the, so basically the net torque acting on the uh, pinion is given by this equation. So now next step is to basically combine these equations by using the fact that the force is basically the output torque divided by R. So then we can basically find out what is the expression for the output torque T out. Uh, so basically m dv by dt plus R into V is the force F, which is T out on R. So we get the expression for the output torque T out from this, so which we can substitute in this equation. So what we get is into d omega by dt is T in minus the bearing friction minus m. Now here we know that the angular velocity omega and the translational speed of the rack are related. So how are they related? So basically they are related through V is equal to R into omega. So then we will substitute this and eliminate the variable omega in the previous differential equation. So basically we can write that d omega by dt is equal to 1 by r dv by dt. So we can substitute this expression again in the differential equation and use the fact that uh, the omega is v by r. So then what we get is, so this is the modified differential equation that we get. Now further we can rearrange these terms, and what we get is basically, so basically dv by dt into ip plus m into r square upon r is equal to t in minus rb minus rr into v. So basically we can rearrange it further to get basically dv by dt is r upon ip plus m r square into t in minus. So this is the final expression for the rack and pinion system. So this is the final differential equation that we get for this particular system. And now further, if we want to draw the bond graph for this system, so what we get is that the source of effort, which is the input torque T in, so that is the source of effort, and So part of the energy is being so the part of the mechanical energy is being consumed in rotating the mass, or basically the inertia of the pinion. So therefore we can write it as a one junction. So and some part of the energy is also being lost in the bearing friction. And then the basically the translatory like the rotary to translatory motion change, we can use a transformer element to represent that. So for that, so basically the conversion factor is basically, so the V is equal to R into omega. So the element the transformer modulus will be basically R. And then the rack, so this basically the rotary energy is being transferred to the rack now. So for the rack, so part of the energy is spent in moving the inertia of or the mass of the rack, and some of the energy is being lost because of the friction or damping. So again we can write it as like a one junction. So the so there will be two elements, so basically the resistance element, which will basically represent the damping viscous damping because of the friction between the rack and the guide, and another bond to represent the inertance or inertia of the rack. So this is the bond graph for the system. Now to assign the causality, so we first start with the assigning the causality for the source. So for the source effort, we assign the causality on this side. And now for the inertia, we have the preferred causality. So we assign the causality here. And for the transformer, we now here we have another one junction here as well as here. So what we can we will have the causality for the transformer element like this, like this. And then the causality for the other two elements, we will show it like this. And finally the causality for the resistance element, we will be representing it like this. So this completes the bond graph for this particular system. So this is how we can use the traditional Newton's second law of motion to derive the differential equations for any mechanical system which involves rotary and translatory motions. So now in the next example, we have to derive a differential equation which relates the input voltage to a DC servo motor and the output angular velocity. So assuming that the motor is armature controlled and the equivalent circuit for the motor has a armature with just the resistance and its inductance can be neglected. So now how do we solve this problem? So for this we first need to understand the general construction of the DC motor. So the DC motor has, so it can have either, so it has a stator and a rotor. So the stator basically involves the field windings. So we can have either uh, coils to coils with a lot of turns to basically create the magnetic field, or we can also alternatively have permanent magnets. So the two poles, so the magnetic field inside the motor is created because of, it can be either created because of permanent magnets or through these windings. So these are called as field coils. And inside we have the rotor, which has the armature windings. So these are the armature windings which are shown by the black dots here. So this is the so now how does the interaction of the current carrying conductor and the magnetic field create the rotary motion? So for that we can basically draw this diagram, so which shows basically the coil, let us say the armature coil, and it is between the poles of either a permanent magnet or the effectively the field windings create like the north south pole directions because of the current passing through them. So effectively we will have a magnetic field from north to south. So this is the direction, and let us say if the current is passing through the armature coil like this, so then let us say this is the direction of the current. So by the general the Lorentz force that acts on a current carrying conductor placed in magnetic field, so we can show the direction of the forces. So here the force acting would be, so for the on the left hand side of the coil the force will be downward, let us call it as F, and for on the right hand side the force acting would be upwards. So these two forces F uh, act are equal and opposite, so they are equal in magnitude and opposite in direction, and these two forces form a couple which will create a torque about the axis of the coils of the armature coils, and therefore which will basically cause a torque acting on the armature, so which will rotate basically rotate the rotor of the electric motor. So this is how the like basically the electrical energy is converted into mechanical energy in a electric like DC electric motor. Now we can draw the general equivalent circuit for the DC motor. So let us first start with the armature windings. So we can model the armature having some certain inductance La, some internal resistance Ra, and the electric motor have now, because of the interaction of the magnetic field, so as per the Lenz law, so there will be a back EMF being generated because of the induced voltage across the armature. So that back EMF will oppose the cause, that is so basically the flux that is being cut through that. So it will induce a, because of the change in flux linked to the coil, so there will be a change in the because of the change in the magnetic flux linked to the coil, there will be a voltage that is induced across the armature, so that is called as back EMF, and it will oppose the cause, that is basically the rotation. So let us say VA is the voltage applied across the armature windings, and then let us say T is the torque output, and let us say omega is the angular speed. So there will be a load so which has, let us say, some moment of inertia I connected to the rotor of the electric motor. And then we have the field windings. So the field windings can be shown as so basically, so the field windings will also have some inductance and some resistance. So let us say IA is the armature current, and let us say IF is the field current, and the potential difference across the field coils, let us say we call it as VF. So now for an armature controlled electric motor, we maintain the field current constant. So IF is, or basically the field current is constant. So then we can write down the differential equations. So if the field current is constant, the magnetic field produced by the field coils, that will also be constant. So now this force which is generated because of the interaction between the armature coil and the magnetic field, so this particular, the torque is basically the force into the width, and this particular force is so basically the number of coils into the magnetic field into the armature current into the length of the coil. So basically the torque is proportional to the magnetic field and the armature current. So we can write basically torque is some constant K1 into magnetic field into the armature current. And similarly the back EMF VB, so that will be proportional to again the armature rotation, like the and the flux linked to the coil, which is again proportional to the magnetic field. So so it is again proportional to the speed of rotation of the armature and the rate of change of flux. So the flux is proportional to the magnetic field. So we can write VB is minus K2 into B omega. Now in this particular, now we can write down the differential equation for the armature using the Kirchhoff's current law or the Kirchhoff's voltage law. So let us write down the equation for the equivalent circuit for the armature. So this is the equation for the equivalent circuit for the armature windings. Now for if the magnetic field is constant, so then we know that we have just written that the back EMF VB is K2 into B into omega. So if so for the armature controlled case, the field current is constant, so therefore the magnetic field is also constant. So then we can write VB is some K3 into omega. So we will get basically VA minus K3 into omega minus IA into RA. And we have also been given that the inductance of the armature coil is negligible, so this term will become 0. So then we will get this as our equation for the armature. And now for the torque, we have derived that the torque is some K1 into B into the armature current. So for the armature controlled case, so we know that since the field current being constant, the magnetic field is also constant, so we can write it as some K4 into the armature current. So now we can write down the differential equation for the uh, rotor of the electric motor. So the net torque acting on the rotor of the electric motor is basically the moment of inertia into change in the angular rate of change of angular velocity will be basically the torque produced by the electric motor and some energy is also lost because of the bearing friction, which we can write it as RB into omega. So now from this we can get the expression for the armature current. So armature current IA will be 1 by K4 into, so now we can substitute this expression for the armature current in the differential equation for the armature winding, so which is minus IA into RA. So IA we can substitute here, so it will be 1 by K4, so RA into, So we can simplify this further. So we will get K3 plus RA into RB on K4 into omega minus. So this gives us the differential equation for the electric motor, which is armature controlled. So this is a first order differential equation. So it is like the differential equation which gives us the relationship between the armature voltage applied and the speed or angular speed of the electric motor. So this is a first order differential equation, so which can be solved easily. So now how do we solve this particular differential equation? So for that we basically can rewrite this differential equation as, so let us denote this as some C1, this as some C2. Then we can write the differential equation as C1 d omega by dt, or we can also write it as d omega d by dt plus C2 by C1 omega is equal to VA by C1. So now how do we solve this first order differential equation? So we have to find out. So this is a linear first order differential equation. So for this we need to multiply by the integrating factor. So what will be the integrating factor? It will be, so we will get basically multiply by this integrating factor e to the power C2 by C1t into d omega by dt plus again C2 by C1 omega. So the left hand side is basically the derivative of omega into e to the power c2 by c1 omega t. So now we can easily integrate this differential equation because it is now in variable separable form. So then uh, what we get is, so now if the variation of the armature voltage with respect to time is known, so then we can further integrate this differential equation to get the exact solution for the variation of omega or the speed of the DC motor with respect to time based on the known variation of the armature voltage with respect to time. Now the next question to which we come to is basically the rate of flow of liquid through an orifice. So this so the general equation for the rate of flow of liquid through an orifice is given by CD into A into square root of 2 into P1 minus P2 by rho. So where CD is the discharge coefficient, A is the cross-sectional area of the orifice, and P1 minus P2 is the pressure difference, and rho is the density of the fluid. So what our task is to derive a linearized flow equation for an orifice of variable cross-sectional area. So, so for this, we know that this particular relation for the flow rate variation with respect to the variable cross-sectional area and pressure difference is a non-linear relation. So now to linearize this, we can take a partial derivative of the flow rate with respect to the area and find the corresponding slope, let us say m1, and then again take another partial derivative with respect to the of the flow rate with respect to the pressure difference, and let us call that as the slope as m2. So then we can write it as partial derivative of q with respect to the area is CD into by rho. And similarly the partial derivative with respect to the pressure difference, it can be written as 1 upon. So these will be the expressions for the partial derivatives with respect to the area and the pressure difference. So let us call this slope as m1 and this slope as m2. So then we can write that the, let us say, the change, small change dq, we can write it as del q by del a into the differential change in the area delta dA plus the partial derivative of q with respect to the pressure difference P1 minus P2 into, so this we can write it as the general differential equation. So therefore the corresponding change in the flow rate, so let us say delta q, we can write it as m1 into the change of area delta A plus m2 into the change in the pressure difference P1 minus P2. So this is the general expression for the rate of change, for the change in flow rate, flow equation for the orifice of variable cross sectional area and pressure difference. So this accounts for both the change in the area of cross section as well as the change in the pressure difference. So the specific, the equation for the slopes m1 and m2 will depend on the particular operating point. So let us assume that this coefficient of discharge CD and the, and also let us assume that the fluid is incompressible, so the density will also be constant. So we can write this flow equation as some constant C into A into root of P1 minus P2. So the slope m1 will now become, so let us say P01 and P02 are the uh, particular pressures at the operating point P0 and P, so, and similarly m2 we can write it as, so these are the expressions for the slopes m1 and m2 as a function of the operating point. So this is how we can derive a linearized flow equation for the orifice of variable cross sectional area. So now this question is like a multiple choice question which is related to the same thing. So we just derived that the rate of flow through the orifice is a non-linear relation which depends both on the pressure difference as well as the area of cross section of the orifice. So therefore the both the equations A and both the options A and B are correct. Now in the next problem, we have been given a electric motor which is being used to rotate a pulley, and this pulley has a flexible rope on which is wound on it, and it is being used to lift a mass m. So the stiffness or and the damping coefficient of the rope are given, the radius of the pulley is given, and omega is, let us say, the angular velocity of the shaft. Then we have to derive the expression for the motion of the mass. So let us say y1 and y2 are the displacements of the two ends of the rope. So the rope is being modeled as a flexible one, so it has both stiffness and damping. So the, let us say we'll draw the free body diagram first of the mass m. So it has basically the force of weight and the spring force and the damping force, and similarly for the spring, it has its own spring force acting on it, and the damper also has its the damping force acting on it. So we can apply the Newton's second law for to get the equation of motion for the mass m. So so the now the equation for the spring force can be written as minus k into y1 minus y2 minus damping force as y1 dot minus y2 dot plus weight. So this is the expression for the motion of the mass. So now further, if we want to derive the expression for the net torque acting on the pulley. So let us say if T is the torque provided by the electric motor, and then the spring force and the damping force will again provide the resisting torque. So this is the expression for the net on the pulley. Which is I into omega dot. So this is how we can derive the expression for the uh, net torque on the pulley and the equation of motion for the mass. Now we come to the next question. So it is given that we have a rotary potentiometer which has a maximum angular span of, let us say, 180 degrees, and the input voltage applied is, let us say, 80 volt. So then the output voltage for a 90-degree rotation, so it will be basically output voltage, let us say we call it as VO. So it will be proportional to the rotation of the, so for a rotary potentiometer it will be proportional to the rotation, which is theta by theta max into the input voltage, which is, let us say, VI. So here the output voltage will be 90 degrees divided by 180 degrees into 80, so which will be 40 volt. Now we come to the next question where we have a hydraulic servo motor. So for the hydraulic servo motor, the relationship between the input xi measured from the central position of the piston of the spool valve and the output is given by what? So now for that, to answer that question, let us go to the lecture slides for that this particular week. So in this system, so in case of the hydraulic servo motor, we have the piston and which is subjected to pressure difference on both sides. So now let us refer to the example on the hydraulic servo motor. So in this figure we can see that uh, there is a piston which is inside the cylinder, and it has inlet and outlet ports over here. So so on the left hand side, the inlet port, the pressure on the inlet port depends on the position of the spool valve, and similarly the pressure on the exit side of the piston also depends on the position of the spool valve. Now to derive the differential equation, so we assume the position of the spool valve, which is when it is at the center. So when both the input and the exit ports for the cylinder both are being blocked by the spool valve. So then therefore there is no flow rate of the oil through these inlet and exit ports. So therefore the flow rate will be zero at that. So the flow rate Q here will be zero at that position. Now when the supply pressure is changed, so then there will be a displacement of the now depending on the supply pressure and the outlet pressure PO, uh, depending on the difference between them, it will decide the direction of the motion of the piston. So if the supply pressure is greater than this outlet pressure PO, then the spool valve will move to the left hand side, and it will basically because of the movement of the spool valve, the spool of that valve, so that will change the opening or orifice opening for the inlet port of this cylinder, which is shown here, and that will cause the corresponding change in pressure on the inlet side, and similarly for the output side of the cylinder. So by have increasing the supply pressure, which will basically cause the spool movement on the left hand side, and then correspondingly that will cause a movement of the piston towards the right over here. So now to derive this differential governing equation for this, so for that what we have been given here is the pressures of the supply pressure and the outlet pressure here. So the pressure on the inlet side is basically PS minus P1 for the pistons, and for the fluid which is leaving the chamber or the piston cylinder is for that the pressure difference is basically P2 minus P naught. So therefore we, as we had derived earlier, the equation of the flow rate across the orifice, uh, which involves basically the variable cross sectional area and the pressure difference. So here for the inlet port and exit port, so we have these equations being derived for which depend on, so the uh, change in the cross sectional area will depend on the movement of the spool valve, so therefore it is m1 into xi. And similarly now with respect to the central position of the spool valve, so then in that case, so the supply pressure and the outlet pressure will be in equilibrium. So then therefore for the inlet port, the change in basically this, so therefore there is no change in supply pressure and the outlet pressure here, so then there will be uh, so the change in pressure on the inlet side is minus delta P1, and for the exit side it is delta P2. So similarly those quantities have been substituted here, and then we add up these two equations to get the equivalent flow rate as a function of the pressure difference on the inlet side and the outlet side of the piston. So, and we equate it basically to the rate of change of flow, which is leaving the rate of change of volume in flow rate across the piston. So, and we also consider some leakage of fluid through the piston, so which is again modeled as the uh, flow rate through a constant cross-sectional area. So from this we get a differential equation in terms of which gives us the variation of the change in the pressure, the movement of the spool valve xi, and the uh, equivalent motion of the piston towards the right or left side depending on the pressures. So now further, when we consider the force force acting on the load which has stiffness and damping properties, so for that if we write the equation of motion and using the basically the net force being exerted by the piston is proportional to the uh, basically the change in pressure difference across the piston multiplied by the area of the piston, so that will be the force exerted by the piston on the load. So that minus the spring force and the damping force will be the net force acting acted upon by the piston on the load. So for that, for this load, we if we derive the equation of motion, so that will be a second order differential equation. And now in this we basically get an expression for the pressure pressure change in terms of the movement of the mass or the load. And so now if we substitute this expression for delta p1 minus delta p2 in this original differential equation which we just derived, so then we get this uh, second order differential equation which has these coefficients alpha, beta and gamma, etc. So we can see that this is a second order differential that we get for this hydraulic servo motor system. So therefore, so the answer to this question, that the relationship between the input and the output, like input motion xi and the output motion xo, is a second order differential equation. Now the next question, let us consider that there is a coil which is wrapped around an iron core. So if the flux in the core is given by phi is 0.5, into sine omega t, and if there are 100 turns, so then the total flux will be number of turns into this particular flux. So the voltage induced across the terminals of the coil, that will be given by, so basically it is given by N into d phi by dt. So where N is the number of turns of the coil. So it will be 0.5 into 100 into omega cos omega t. So this is the expression for the voltage induced, which is basically 50 omega cos omega t. Now in the next question we have been given that there is an orifice meter which has an orifice diameter of 10 centimeter. It is inserted in a pipe of 20 centimeter diameter. So the pressure gauge readings upstream and downstream, they are basically 19.62 Newton per centimeter square, and so therefore we have been also given the coefficient of discharge. So we have to find out the flow rate of water through the pipe. So we already know the expression for the flow rate of water is, so basically the density of water is basically 1000 kg per cubic meter, which is basically 1000 into 10 to the power 3 into grams per. So the flow rate is basically 0.6 into, so the area of the orifice will be, area of cross section of the orifice will be pi by 4 into, so this will now be in centimeter square. So now these are readings in Newton per square centimeter. So we need to convert them into Newton per meter square. So for that we need to multiply them with ten to the power 4 into, so to convert them into Newton per meter square, and the density in SI units will be 1000. And now to convert this area into the into basically into meter square, so we need to multiply this into 10 to the power minus 4. So this will give us the flow rate. So by calculating, so we can do these calculations and find out the equivalent flow rate. So it's basically just substituting these quantities, which you can try it on your own. Now in case of a DC motor, the back EMF, it depends on the rate of rotation of the armature as well as the flux linked with the coil. So the back EMF is basically written as some constant into the magnetic field and the speed of rotation. So therefore it depends on the rate of rotation of the armature as well as the flux linked with the coil. So therefore the correct answer to this question is both A and B. So now in this question we have to select the correct option for the potentiometer. So for the potentiometer, so input is, it can be either linear motion or rotary motion, and we get the corresponding potential difference depending on the linear or rotary motion. So the it can be basically the option B as well as C. So the correct answer to this question is both B and C. Now next we come to this question where we have to find out the inertia tensor for a rectangular body of uniform density rho with respect to the coordinate system. So here we have to find out the each of these each of these terms, like which is the product of inertia and the moment of inertia about the each of these axes. So the general equation for the moment of inertia is basically integral. So for any given differential element, it is integral r square into dm for any infinite decimal mass. So let us say if a particular mass is located somewhere here. So the so let us say we consider a mass small dm which has some dimensions, differential dimensions, let us say dx, dy, and dz. So the mass of this differential element will be rho into the mass into the volume mass, which is rho into, sorry, dx into dy into dz. And the position vector, over here is, so let us say if we consider for the moment of inertia about the axis x, so I x, so this will be the expression for the moment of inertia about the x-axis. So the limits of integration uh, are basically for x 0 to w, for y the limits are from 0 to L, and similarly for z it will be 0 to h. So now if we solve this third integral now, so it will become w into rho. So if we take out h into L outside the bracket, so then we will get w into h into L into rho. So this product w into h into L into rho, so this represents the mass, so which is m into L square plus h square by 3. So this is how we can get the moment of inertia about the uh, axis. So this becomes mass, so volume into density, which is mass into L square plus square by. Similarly, we can, so now to get the other inertia components across the other uh, the axis x, y, and z. So we can use the similar approach. And similarly, for the product of inertia, we can use the similar kind of approaches, and we can determine all the 9 components of the inertia tensor. So that's how we can basically determine each of the components of the inertia tensor. So, and we can use basically a similar approach to find out the inertia moment of inertia across each of the axis x, y, and z. And similarly, we can also find out the like the off diagonal elements x, I would like basically the product of inertia terms here, using the appropriate expressions for that product of inertia, and we can determine all the 9 terms in the inertia tensor. So that's all that I had from my side for this week's problem solving session. So I hope that this session helps you in solving the assignment problems for the fourth week. So thank you very much.